Hello everyone, my name is Durbar Roy. I'm a PhD student working under Professor Saptarishi Basu, and I am one of the course TAs for the course Statistical Thermodynamics for Engineers. So, in what we are doing here is we are providing a set of parallel lecture materials, supplementary lecture materials that will go as a that aside, and I will say it provides the mathematical basis and mathematical preliminaries that will be required to strengthen our understanding of statistical thermodynamics in general. So here we will be covering a lot of mathematical concepts and topics that we'll be using in the main lecture series quite a lot. Okay, so here we'll be discussing ideas like operator theory, various kind of coordinate systems, eigenvalue problems. Okay, so overall the flavor of these discussions that we will be having is like it will be very much intuitive, and what we will trying to do here is develop the mathematical and physical intuition required to understand statistical thermodynamics in general. Further, we will be also doing a lot of problems from different sections of the course materials so that the concepts are understood better. And overall, I hope that what we are trying to provide here is uh, to better understand the main course content, the main course statistical thermodynamics. As we will see, statistical thermodynamics has a lot of mathematical concepts, especially in probability theory, operator calculus, in general. Okay, so we'll be beginning our uh, uh, sessions by a series of introductory supplementary videos on operator theory in general. Okay, so let's start by understanding what operators are in general. Okay, so let's start by having this our basic understanding of operators in general. So the topic that we'll be discussing is operator. Okay, so to have a better understanding of what operators are in general, let's start with something more basics which we already know. So we do our recap from our previous mathematical studies of, let's recap what do we mean by a function. Okay, so let's say we are what we are when we studied our single variable calculus, we studied functions of a single variable, of a single real variable, let's say real variable. So we write an expression of the form, let's say y is a function of x. So what this statement was all about. So this said something like we can think of this function f as a mapping from a set of input to a set of output. Okay, so in case of a real variable, what is the input? So the x belongs to the real space, the real line, you can think about the one-dimensional real line. So, and this goes as an input, goes as any real number you can take as an input to the function f, and that provides an output y is the input. The set of all inputs is called the domain, if you remember. All inputs is the domain, and it produces a real number. So this y also belongs to a real number r. And set of all outputs what we call as the range of the function f. Okay, Another way of understanding this, the same idea is of thinking the function as some kind of a machine. Let's say we have this function f as a machine f, so it takes an input x and it provides an output y. Okay, so that's another way of thinking about this function. So it takes a real number. Let's say it takes let's take a specific example. So let's say example, we have a function, example 1, we have square. So this is a squared function. Okay, so what it does is, this is a function f x square. What it does is, whatever input you give, squares it and produces an output. So let's say we put the number 2 as an input, the output is 4. Provide the number 3 as an input, the output is 9. Okay, so it's squaring. So you see it's doing some kind of an operation. Okay, so here we'll see how the general idea of what do we mean by operation, and hence operators will come in handy. So we'll be realizing later that we can think about functions also as some kind of operators. Okay, but we'll building the actual concept of what we mean by operators are in the most generic fashion. Okay, let's take another example where, let's say we have another function g of x, let's say is the square root function. Let's say, so what it does, again let's think about it in terms of some kind of a function machine. So it's the root. Okay, so it takes an input, let's say it takes the input 4. Okay, and let's say what it does is provides a positive value of it. Okay, so gives the output 2. Okay, similarly what we can do is, let's say give it an input 9 and it gives us an output. So these are examples of what we know as a single variable functions, which we studied in our single variable calculus course, where you take a single input x from the domain and it generates an output, a single variable again in the range set. Okay, that's what we mean by function of a single real variable. But this idea of functions can be, as we know, could be generalized to higher dimensions. So let's say we have a function of two variables, f of comma y, and that provides an output which is that. So now here you see the domain is, so x can be any, let's say again we are dealing with, let's say, real variables, just can be any real number, y can be any real number, and the output is can also be any real number, let's say. So if you see the domain is a tuple. So the domain, if you see, it's so the set, so what we are providing is a set as an input. As you can see, it's a tuple, it's a set xy. Okay, so that is, the domain belongs to the R2 space, but the output, the range, as you can see, is in R1 space. Okay, so that's what the idea of, let's say, a two variable function of two variables. So you need two numbers as an input and it gives a single output. Example of this is, for example, the f of xy is, let's say, the distance function, or the square distance function from the origin. You can think about this as some kind of, again, some kind of a machine f, which calculates the square distance from the origin of coordinates, Cartesian coordinates. What it does, it takes two inputs and y, and it provides a square distance as an output. Okay, so let's say you give it 0 0, provides the output 0. That's telling the distance of, so the distance is 0 because you are right at the origin itself. Distance is measured with respect to the origin. Let's say use the same function and you give it the 0.12. So you see the input is a set x comma y that you are giving, so it's coming from a two-dimensional space, okay, R2. And so once you give the 0.12, it will give you the output. It's 1 square plus 2 square, so that's 5. That's the square distance from the origin and of the point 1 comma 2. Okay, so that's the generalization of a function in 2 dimension, and this generalization can be done in higher dimensions. So for example, the functions can be f of x1, x2, x3 dot dot n. This is a function in, let's say, n variables, okay, and the same idea holds. So you give it a n tuple now, so this is now an n tuple, and it provides a single real variable as an output. So this is a real number, okay. So this idea of a function of where you're taking n inputs, let's say, can be thought of in a slightly different manner, where let's say now we have, so let's write this tuple in a form of a column vector. Let's say we write it x1, x2, x3 dot 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 xn. This is a n cross 1 column vector, okay. And what we do with this is we do some operation on this, okay. That means we pass it to some kind of a black box, some kind of a machine. We don't know what that it is, and what it generates is not a single number as before, but it generates a series of, again it generates an n tuple, let's say, but again generates a vector y1, y2, y3 dot 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 yn in general, okay. So what it does is it takes a vector as an input. This is an input to this function, and it generates a vector as an output, okay. And from our previous understanding and previous studies of linear algebra, we know what kind of mathematical object transforms a vector into another vector. It's a matrix, okay. So a matrix transforms one vector to another, okay. So we can rewrite this in a different mathematical form. Let's say this input vector we call by x, the matrix by m, and the output vector by y. We can write this as the matrix m acting on the vector x gives us the vector y. We can see that we can think this also as the matrix m operates on the vector x to provide the vector y, okay. So you see how this generalization is happening, right from a single variable system to two-dimensional to n-dimensional and to matrix vector operations. And if we continue this generalization further, we come to a realization, okay, so let's say what happens when we ask the question, what happens when the n goes to infinity, or that is, we are dealing with the infinite dimensional vectors, So as you see, the logic remains the same. So we have some kind of an function box, some kind of a black box. It takes an infinite dimensional vector. So now we need a very useful mathematical realization that an infinite dimensional vector can be realized as a function. Okay, given that this realization we have, so we can think about operators, okay, that take infinite dimensional vectors, or to say, let's say it takes function as an input. This is now continuous. Now you see what it is taking. It is taking a continuous object. Okay, so it's an infinite dimensional in that sense, and it gives out a function as an output, g of x, and that is what we mean by operator. Okay, so this is the kind of operator that we wanted to come up the main concept of. So this is the generalization that we were looking for. So an operator A is an object that acts on a function f, okay, to produce another function as a result. So that's what, so here A, this is the operator that we were looking for. Okay, so that is the generic idea of what we mean by operators in general. Okay, so that is the general idea of operators that we wanted to come up with. So an operator is an object A hat, here that is written as A hat, and it acts on a function f of x to provide us another function g of x. So you see how we came up with the generalization right from the idea of from a single variable function to multiple variables to, let's say, n variables, and through the idea of a matrix vector operations to the idea of a continuous operator that we are discussing. A very important point to keep in mind, for example, here is when we're dealing with functions where the inputs were discrete non-continuous objects, like let's say a single variable, two variable, and n variable, the domain set, you see, that was set of all numbers, and hence it belonged to, let's say, R1 space, R2 space, R3 space, and so on. On the other hand, now for the idea of the operator that we are discussing now for A hat, so you see the set of all inputs is known as a function space. Okay, function space, not just all inputs but also outputs, the set of, like, so what we are dealing with is we are picking functions from a space of functions. Okay, and one of that elements of that function space is, let's say, f of x, and you pass it through the operator A, and it provides another function g of x from g of x, and that g of x can be on the same function space, or it can be on a different function space, and we'll be seeing all these things as we require different ideas related. Okay, so but that is a generic idea of operators that we wanted to come up with. Okay, so now we will be discussing some basic rules of operator algebra, some basic rules of operator algebra, and this, I think so, we will be familiar from our previous understanding of, let's say, of thinking about, let's say, derivatives and integrals as operators. Okay, so let's write down the rules. So let's say operator A hat acting, let's say, on c times f of x is same as c A hat f of x, where c is a constant, and c is a constant. Okay, similarly, let's say we have two operators, A hat, B hat, and the sum, if we sum up both the operators, and when we are thinking about sum, that sum has to be very, very specific. That means these two operators needs to be should be able to add to each other. Okay, that's one way of putting it. And you put it and operate on the function f of x, that is same as the operators acting on f individually and then summing the result. Okay, that's another property. Third is a property, let's say you do the product of an operator and you generate a new operator, operate that on a function f of x, that is the same as, let's say, first you take the operator b, act on the function f of x to generate some kind of an operation, and then take that as an input to the operator a, and you should get the same result. Okay, similarly, this property that now we will be writing, let's say we have an operator a plus b plus operator c. This is same as operator a plus operator b plus operator c. So this is the associative law for addition. And then we have, let's say, a plus b equals b plus a. Okay, so that's you can think about the commutative law of commutative law with respect to addition. Okay, and you see a plus b is same as b plus a, but as we will see later that this is not true for multiplication operator. That means keep in mind, we will be discussing this later, but a hat b need not be equal to b hat a, and this will come in this will play a very important role, and this plays a very important role in quantum mechanics, as we will see later. This is called the non-commutative properties of quantum operators, some of the quantum operators. Okay, and then we have some special operators that we can draw parallels with from linear algebra, as which we call, let's say, the identity operator I hat. So we can think about this as a parallel with the identity matrix. It acts on a function f of x and it returns the original function back, f of x. Okay, so this is the identity operator. And then we have the null operator, where what it does is act on a function to produce 0 as an output. Okay, so those are some of the very important properties of or I will say the basic rules of operators that we will be discussing. Okay, extension of these ideas and a very important property and a very special class of operators that we'll be dealing with specifically in quantum mechanics is what are known as linear operators. Okay, linear operators. What are linear operators? So linear operators are those operators that satisfy the following rule: a hat is linear if, right, a hat is linear if it satisfies the following: a hat acting on the function f1 of x plus f2 of x is the same as it acts on individual functions. Okay, and you sum up the results and you should get the same result. That's called the idea of linearity. Okay, and then basic extension of the idea of this linear and combining this rule 1 generalizes the idea of linearity. And just by thinking about, we can write this in terms of, rather than just now the function, we can think about it's multiplying by some kind of a constant on x, plus let's say another constant beta f2x, and what we should get is alpha a1 f1x plus beta a f2x. Okay, so as you can see, what we are doing is linearly combining. These are linear combinations. Linear combination. Okay. That's what we mean by linear operators in general. Okay, so what we have covered in this lecture is what we saw the idea of what a general operator is. Okay, what a general operator is. We have understood what do we mean by an operator acting on an object. We get an understanding of what are function spaces. We saw some basic rules of operator algebra, and we understood what do we mean by linear operators. Okay, so we will be covering the remaining things in the next lecture. Thank you.